Welcome grade 11s. This is physical science. My name is Gillian, and today we are going to look at the big topic, the resultant vector. We're going to look at the big ideas, and we're going to see that it's actually not so scary. Okay, so let's have a look at the overview of today's lesson, and we're going to see what we will cover. So on the screen, here's the big word, the resultant. And we are going to look at that in terms of vectors and scalars. So what are they? What do they look like? What do they represent? Then we're going to look at forces, because forces are really important in our physical world, and we relate vectors and forces, okay? Then we're going to have a look at component of forces. So if we take a vector and we break it up into its components, what does that look like? We have got two scenarios. We've got one where an object's on a flat surface, and we have another scenario where an object is on an incline, on a slope. So we need to unpack that a little. We need to learn our definitions, of course, and then we're going to look at what is a Cartesian plane. Isn't that interesting? Okay, so let's get going with what are vectors and scalars, because these are foreign words. You might have heard them in the past, but they really are a bit tricky to try and get our heads around. So scientists, physicists, like to study things that we can't see, like forces. And to be able to represent the things that we can't see, we use what is called a vector or a scalar. So everything is classified as either a vector or a scalar. Now, a vector is something that has got a size, a magnitude, but it also has a direction. That is really important. A scalar is something that has a magnitude, a size only, but does not have the direction. So if we look at my screen, we've got these two words, the vectors. So vectors have got size and they have magnitude. Size is magnitude, and so size or magnitude and direction. So there we go, the direction is really important. That's why I've said "and" in capital letters. Scalars are the ones that have a magnitude or a size only. So what would be an example of a scalar? Okay, I'm going to draw a person for you. So here's a person. I'm not really good at drawing so well, so there's our person. Okay, we better give him some arms. Now, a person has mass to them. In other words, there are atoms of various kinds, molecules of various kinds, and they all pack into our skin, right? Our skin is obviously part of that. They are matter, they make up matter. So we are made up of atoms, molecules, and we call that matter. So we have a certain mass. Depending on who we are, we will have a unique mass. So a scalar is something like mass. It is always a positive value. We can't give it direction. How can we give our mass a direction? There's no direction involved with this thing of mass, this quantity of mass. So this is definitely going to be a scalar thing. What about if we take the mass and we work it through gravity? So we have something on Earth which is the gravitational force. It is the pull of a body towards the center of the Earth. And we know that as a force. It is called a force. It is this, it's a non-contact force. We'll go into that a little later. But if we jump up in the air, we are pulled back down to the surface of the Earth. If we jumped up and we started floating around, that could be quite weird. So we have a force acting on us towards the center of the Earth, and that is called the gravitational force. We represent it by F and G, gravitational force. Now, what does that mean? That means that our bodies, there's this little person again, our bodies are pulled towards the center of the earth. This is the earth. Okay, pretend that that's the earth. So that is the force with which we are pulled towards the center of the earth. It is known as weight. So here's this word, weight. We call it weight in the science world, in the physics world. Weight. Secular world uses weight in a different context. We use weight as in we are talking about the force. And Fg is equal to this thing, the mass times the gravitational acceleration. Can you see that that has a value? So it has a size, it has a magnitude, but it also has direction. We are not pulled upwards, we are pulled downwards. And so that is a vector. So this force of gravity is a vector. Why is it a vector? It's a vector because it has magnitude, it has size, and it has direction, which is down. Okay, I hope that clears up the difference between a scalar and a vector. So the vector is the name of a quantity, an entity that has both size, magnitude, and a direction. A scalar is the name of a quantity or an entity that has a magnitude or a size only. Good, let's move on now. I've spoken about force. Force is very common in the physics world. We almost associate a vector with a force because all forces have got a magnitude and a direction. So when we speak about vector, our brains automatically go to the word force. So what is a force? Well, a force is a push or a pull. So we can either push something or we can pull it. But most forces in our universe, in our world, are either a push or a pull. They definitely have a size. So if you think about pushing your friend on a bicycle or on a go-kart, you are exerting a force. So there is going to be a size to this, a magnitude. It definitely, all forces have a direction. So the force is exerted in a particular direction. And so that is why forces are associated with the word vector. The forces are vectors. How do we represent then a vector? What do we do? How do we draw it? So these things are particular to size. So when we are representing it, we draw a line, and we would have to use a ruler for this. I can't on my screen, so pretend that's a straight line. The length of the line is going to tell us about the magnitude, how big it is. So this would be a reasonably big vector or force. If we have half that amount, then we would draw a line that is about half that line. There are two ways that you draw these. As a sketch, like I have done, with a reasonable, you can see it's like you eyeball it, you can see one's longer, you can see the other one's about half of that. Or you can draw it to scale, which is a very particular, precise way. We use a scale. We say 1 centimeter equals, let's say, 10 newtons. That's the kind of scale you could use. That's very precise. This is just an eyeball sketch, if you were. Now we have to represent a direction as well. So we would have to put an arrow. So an arrowhead would tell us the direction. So that's the arrowhead. That one would be in the opposite direction. Okay, so we get a sense of forces. We've got two different kinds of forces. We've got a non-contact force, which you would already be aware of. Gravity is one of them. Electrostatic force, that's with electricity and with charged particles. And then magnetic force. These are all about a field, so a force field. They're all about a field. We can't see a field, but they are there. We see the effect of a field, an attraction or a repulsion. Gravity, you might say, but we connect it to the earth. Yes, so these non-contact forces can be where objects are close up, but they also act over a distance, so non-contact. Now, the contact forces, there's some strange words there. Contact forces are where two objects have to be touching. They have to be together in order for the force to exist, to be felt. So the first word here is a normal force. We're going to have a look at what that is. A tension force, a friction force, and an applied force. So those are all forces that come into play when the objects that are touching. Let's look at those forces in a little bit more detail, the contact forces. So what is a normal force? Well, a normal force really does depend on the mass of the object. So if we have, I'm going to draw this, I'm going to draw a person, okay, and the person is standing on the ground. Now, that person has a mass, and the person would be pulled towards the center of the earth, and that is the gravitational force, which we've seen is the same as mass times the gravitational acceleration. Now, that person would exert a force on the ground, which is the same as the gravitational force. The ground then exerts a force back onto that person. So let's read the definition of a normal force. A force with a surface exerts, let me read that again. A force which a surface exerts on an object with which it is in contact and which is perpendicular to the surface. So we're talking about a force which a surface exerts on an object that it is in contact with. So this person is in contact with the ground. The ground will then exert a force up onto that person, and they are perpendicular. So here's the surface. The surface is that way. The force is that way. It's perpendicular, 90 degrees. So the normal force would be the force exerted back onto that person. Where those feet are sitting or are standing, the force would be exerted up onto the one foot and up onto the other foot. Tension is when we pull something. So tension is in a rope or in a string, like tug of war. That would be tension when a rope or some sort of cord is being pulled in opposite directions. Friction is a very interesting force. Friction opposes motion. Here is what it says: a force that opposes the motion of an object and which acts parallel to the surface. So I want you to imagine that you are running and you fall on the grass. You are going to get a grass burn if you've got shorts on, maybe on your knees, or you could even be on your side. And so what is happening there? Well, you are sliding along the surface. The grass, is acting in the opposite direction. It's trying to oppose your motion. It's opposing your motion. You're going this way, the grass is moving that way, and it burns. So friction is about heat. There's heat between the two surfaces. Two surfaces come together, it's a contact force, there is a bit of rubbing, and there's heat. So that's why in the winter days, winter mornings, you rub your hands together. It gets warm because there is heat being produced. Then we have an applied force, and the applied force is either a pushing force or a pulling force, and we need to state which one it is. So an applied force would be you pushing your friend on the go-kart, or dragging something along the ground. That is an applied force. Right, grade 11s, we are going to take a quick break. When we come back, we'll do some more. Welcome back, grade 11s. Right, we're going to take a quick look at what forces do. So on my screen, we can see that forces start an object moving, okay? They do that. What else do they do? Well, forces can speed up an object, or they can slow it down. They can also stop an object. They can change the direction of an object. So imagine you are playing soccer, the ball comes towards you, you can change the direction. The ball's coming towards you, you put your foot out and you kick it to go that way. That means you are changing the ball's direction. What about changing shape? Oh, this is interesting. So when you were little, you might have had Play-Doh or stress balls. You can push them, you can change its shape. If you're jumping on a trampoline, that trampoline changes shape, doesn't it? So forces change shape. They can also rotate objects. If you've ever taken a bucket and filled it with water and swung it around, okay, that's you. You are rotating the bucket. Right. Let's get on to the real nitty-gritty, the big idea about the resultant. So if we have a vector, and this is a force, the force vector, you can see I've drawn it in purple over here. There it is there. These are forces that are now acting at an angle. So we speak about components of the main vector. In other words, we can call this vector, this purple vector, we can call it the net force. I'm going to write it here, net force. Or we could call it the resultant force. It is possible to break this force up into its components. So it can have a vertical component, one that goes this way, and it can have a horizontal component that goes this way. So you can see now this force is at an angle, the vector is at an angle, look here, you see there's the angle, it's not straight. It's not straight horizontally, it's not straight vertically, it's at an angle. We can take that and we can break it up into its components. And we call them the horizontal component and the vertical component. So here on my diagram, you can see that there is an H, and that stands for the horizontal component of force. This is a force, we're dealing with a force. Something is being pulled. This one over here, there's a V, and that stands for the vertical component of the force. So as we take this force that's pulling this box, as we take this force and divide it up, break it up into its components, we can also say that those components, when they are put together, make a net force or a resultant force. So if we add the horizontal components and we add the vertical components together, we will get this net force or this resultant vector. It is the vector that can replace the two components completely. So we've got this component, we've got this, I know my arm's a bit weird, this component, we can take those components away and replace them by a single vector, which is then called the resultant. Now, these horizontal and vertical components can be calculated if we know what that net force is, what the resultant is. And likewise, we can take if we've got the knowledge of the horizontal force component and the vertical component of force, we can take that and put them together to find the resultant force or the net force acting in this case. Next example or next scenario of having components of a force or components of a vector. Instead of having a force or vector that is at an angle, we have the surface which is at the angle. And you can see here that we have a slope. So the surface is sloped. There is a body or an object on that slope, and there is going to be a resultant force acting on that object. Usually when an object is on a slope, it slides, and it normally slides down. It's very seldom that it slides up. It will only go up if it's being pulled up, right? So if it's sitting on that slope, it's going to slide down that slope. So there is a resultant force or a resultant vector acting on this object. And it is here, I have labeled it Fg. We've spoken about Fg. It is the gravitational force. So gravitational force, how do we calculate that? It is equal to the mass of the object times by gravitational acceleration. We can take those, well, that force, that resultant force, and we can divide it into its components. Now, these components are named slightly differently. They are named according to their relationship to the surface. So here we have, if you look at this dotted line that way, we have a component which is parallel to the surface. You can see that there. So we call it this. It is the parallel component of the gravitational force. And if I move it down, transpose it, I move it down to draw it over here. I don't know if you can see. Let me just change my pen color so that you can see it more clearly. You can see over there, that's better. You can see it's been moved down. Okay, it's been taken from where it's been drawn, and it's been drawn down below so that it touches that resultant force. What about this component? You can see that it is perpendicular to the surface. So we call that the perpendicular component of the gravitational force. So here we're going to write perpendicular. That is the perpendicular component. And you can see it's written like this. It's the perpendicular component of the resultant force, which is the gravitational force. This one here, which we've redrawn over there, is the parallel component. Okay, can you see that when we redraw these forces, that we create we draw in a 90 degrees triangle? That is important for trigonometry, and we use these to do calculations. Okay, so let's have a look at our definitions. The components will add up to the net force, and that is also called the resultant force. So what is a resultant? It takes the place of or has the same effect as two or more vector quantities. So the resultant is a vector, and it has magnitude, and it has direction because it is a vector. And so that line will represent the magnitude, and the arrow will represent the direction. I have time to show you the Cartesian plane really quickly. So this is a Cartesian plane. You can see it. It is an x and a y axis. You can see that it's made up of blocks that are of the same size, and it has got negative and positive values. You've seen this before in mathematics, so it shouldn't be unfamiliar. It should be familiar to you. You'll see that it has two planes. It has the x-plane and it has the y-plane. So we're talking about vertical plane and the horizontal plane, and we use this when we solve problems to find the resultant vector or the resultant force. We are going to continue with this in the next lesson. It is the consolidation lesson, so I hope to see you there, grade 11s. See you next time.